Hello everyone, my name is Andrey. We're going to be talking about today simulating the feasibility of the South Crofty Mine restart plan. I am the CEO of Amalgama Software Design, the company behind MineTwin. MineTwin is a software tool that helps open pit and underground mines around the world to build simulation models to support better decisions. And I'm joined today by Jaco-Ben Vosloo, who's probably one of the most knowledgeable MineTwin experts in the world. So, necessary disclaimer that I need to make. Basically, it says that South Crofty Restart project is an active, evolving program with regularly updated targets and assumptions. And this presentation may contain content may differ from latest stakeholder commitments or published information. And if you need some official, up-to-date documents or any information, you're free to reach out to South Crofty website. With this out of the way, let's get started with the presentation contents. First, I will take about the key stakeholders of the project. Then we're gonna overview the mining process at the South Crofty Mine. Then this will take us to describing project scope and objectives. Then we'll have a little discussion about why we use simulation, why was it necessary. Then we'll talk about project approach, input data. Jaco-Ben will do fascinating demo of our model, and then we'll talk about verification validation, and then we'll discuss the results that we have achieved. The key stakeholders, Cornish Metals is the company who owns this South Crofty Mine. They approached Tamaki, which is mining consultants based out in South Africa, and then they decided to use MineTwin to create the simulation model of that mine to drive the support of better decisions. So the background is that there is an existing underground tin mine in Cornwall, UK, last actively mined in 1998. They use some mining methods, and if you're not familiar with the terminology, fear not, I will cover the process in the layperson terms. And then this mine is planned for redevelopment with support of the British government. And this picture here shows a member of a British royal family, Princess Anne, visiting this mine. I think it was in May 2025, so that kind of emphasizes the importance of the entire enterprise. And to support that redevelopment, a static mine plan was created in industry standard tool. It was Desert this time, and that plan basically included tonnages of ore and waste extracted by years, and probably split up by months as well, and then equipment units required for every year to sustain that mining rate. Let's talk about a little bit about the mining process. So what is basically a mine? A mine is basically a hole in the earth. So, but that is the level of abstraction that probably wouldn't work for our project. So that is why we need to throw in a little bit of details. So the extraction itself is done in underground tunnels, which are called stopes. The process is like, first we use the drilling rigs or drilling machines to do the drilling. Then we use chargers, and the charging team charge the blast holes, and these holes that we have drilled are called blast holes. Basically, they put the explosives into there, then they do the blasting. Like for this brevity, I didn't draw the blasting here. Basically, it would be like a huge fire across the whole slide. And then after we blast, the ore gets crushed and then gets ready for further transportation. And then LHD is like an excavator or scoop tram, take the ore from stopes to cross-docking points, and then at these cross-docking points, the ore gets transloaded onto the trucks, and then the trucks take the ore to ore passes. At the very bottom of the ore passes, there are crushers, and then we hoist the ore using the skip hoist, which the schematic hopefully explains clearly what the skip hoist does, and then we transport the ore on the surface up to the processing plant, up to the surface crusher. And that is the production mining. Production mining is actually extraction of the useful ore, but to get to these areas inside the ore body with the useful ore, we need to do something called development mining. Development mining is basically the same, but it's creating access tunnels from the shaft area to the area where to the useful ore body area. It's pretty much the same, for the exception of that we do drilling forward rather than upwards, and then we take the waste out of the development mining areas and take it to the waste storage. And that static plan that they created with their industry standard tool, it didn't consider, at least properly consider, viewing the fact that the most of the resources are shared. Skip hoist shares its capacity between hoisting ore and waste, and the majority of equipment units could be used in different mine areas and can be shared between production and development works. And also, it didn't properly consider mutual equipment waiting and all the ramifications of them, and then unplanned delays. So that takes us to scope and objectives. So scope is basically what I described you, and there were three main objectives for this project. The first is to validate the restart, the mine restart static plan, and then identify key operational constraints and bottlenecks and foresee where these bottlenecks would or might appear. And then optimize fleet sizing and allocation, basically figure out whether the number of equipment units will be enough for each year, and if so, where should be allocated, if not, how much more we might need. So a little bit of illustration that dives into the question of why it is necessary here to use simulation. So let's focus on just this area and on a very simplistic example. So we are just focusing on what is called haulage or mucking and haulage. Basically what happens here is we have a stope and we assign 2 loaders and 2 trucks to take the ore from the stope through the CDP over to the ore pass. Traditionally what they do is they do the static calculation. If they know what's the shift duration, what's the number of equipment allocated, what's the size of the truck, etc. They do some static calculation to actually come up to the number that they use in their static plan. So in the perfect world scenario, this sub-area of the mine will be able to produce or to transport 1,371 tons per shift of the ore. Then if we factor in 95% availability, which is the real number they use, it goes down to 1,300 roughly. Then if we factor in waiting time, we know that there will be inevitable waiting inside the process because we have changing haulage distances and many other factors. Then we come to 12,000 roughly tons. But what if we simulate that? And this is a screencast taken directly from our MineTwin simulation tool. That basically shows the level of detail we're doing everything. We have 2 loaders and 2 trucks taking the ore from the stope through the CDP to the ore pass. And then we simulate the true 95% of availability for all 4 equipment units here. That is represented with the dark red blocks here on the Gantt chart. And if we simulate that, we'll find out that the achievable production volume for shift is just 1,130 kilotons instead of something like 1,200 kilotons that we assumed in the worst case static calculation. Why would that be? If we do some real analysis, like real world analysis, that we'll see that if we statically assume 95% availability and do this simulation of this ideal case, then the system very soon enters its steady state, and there's only certain amount of delays, which is the lost time, around 20% each delays for the trucks and 0% delays for the loaders. Whereas if we do the real simulation of that system, we will find out that 95% availability in the form of scattered delays throughout the Gantt chart result in the fact that those delays propagate through the system, resulting in much greater fraction of lost time for both loaders and trucks. So in addition to reduced availability on the right-hand side of yours, we have much more lost time that is a result of the system that delays and waiting times constantly propagating through our system. At this point in time, I will hand over to Jaco-Ben.
Thank you, Andrey, for that insightful example. So I'm going to quickly discuss some of our the typical phases that we go through in a MineTwin project and what's the durations. So normally we start with some pre-project phase where we give the client a MineTwin questionnaire and some master data request, and this typically takes about a week, and that gives us the initial information to make sure that when we go on site we ask the right questions, we gather the right data, etc. So the first phase, we spend some time on site, we analyze exactly what's the objective, we interview some key stakeholders, and we define the study concept, like what are all the experiments that we want to set up. Then we take about 3 weeks to do some data gathering and some software adjustments. So something that's maybe unique for MineTwin is that we create bespoke versions of MineTwin for our customers, and you'll see that in the demo. And there we can enable or disable certain pieces of functionality. We can put in proprietary logic. We can add unique things for their specific site inside their version of MineTwin that's still based on the generic MineTwin version. So it takes us about 4 weeks till we get a working model. And then you need to get into the verification and validation phase. And this is usually done through the following 3 steps. So we run the baseline scenario. We change maybe some of the input data, we change some of our assumptions and simplifications, and usually this is a very iterative process until you get to that validated model, and that normally can take another 4 weeks depending on the complexities inside the mine, the availability of the data, etc. So about 8 weeks in total since you've been on site until you get a validated model. And then we start with the scenario analysis, and the objective here is to get to all the simulation experiments and studies that you require to answer their specific questions. So if we start off here, we start off with the scenario design, and then we do usually one of these 4 things. It's either some sensitivity analysis, so you take a specific parameter and then you vary it. Let's say it's the fill rate of the trucks, or it is some speed parameter underground, and we change it from 10 kilometers per hour to 15 in steps of 1, for example. Or we do scenario comparisons, so completely different scenarios, different mining methods, different layouts, different priority mechanisms for the blocks or the stopes that you'll be mining. If you're simulating the sensitivity of a specific number of pieces of equipment, you'll do a fleet sizing analysis, and I'll show how we actually compress this time by having predefined experiments inside MineTwin where you can do this automatically. And then we also have a constraint analysis where we try and determine where is the constraint in your mining operations. Is it the equipment, what piece of equipment, the blocks, etc. So it's also an automated experiment that we've got. And this is also an iterative process. We will go through this many times until you're happy with the experiment that you've set up. And then we end off with conclusions, recommendations. Normally, like for this project, it was a big report that we provided, or it can just be a presentation or some workshop that you do with the clients. Normally takes another 3 weeks. So overall 11 weeks, and the first week that we do as part of the pre-project phase, about 12 weeks in total. So for this specific project, we actually just started this month with the 3rd stage of this project, so like the 3rd iteration where we're doing an analysis for them. And this is specifically on the underground to surface operations, which I'll talk a bit more about later. So what's the key data that goes into MineTwin and where do we get it? So our first question is, what do we know about the physical mine? The layout, the characteristics of the reserve, the geology, the stationary assets that we've got. So these are typically like the coordinates of the center lines of all the roads and the tunnels, the mining areas, what materials, if we're going to model to that level of detail, lives inside the ore, what's the location of the stopes, if we're modeling their grades as well, the haulage destinations like the crushers, ore passes, the skip hoist, your cross-docking points or your muck bays. The next question is, what equipment do we use inside this physical layout, inside this physical structure of the mine? So equipment types, the models, the schedules, and availability, etc. So we'll start off with what's all the models of the trucks, what's all the equipment units, and we can assign them by mining area, shift patterns, blasting schedules, planned unavailability periods, lunch breaks, safety talks, whatever. Time-based planned maintenance events, like if it's work-based, like engine hours, or it's time-based, or it's maybe distance-based, like replacing tires, for example. And then unplanned unavailability events, which would be random events that occurs, like failures. And the last part is what's the volumes that we're trying to reach. So this would be your targets for ore and waste. And if you do ore, we can also include the grade that you're trying to target. And where do we get this? So the physical layout for this specific project comes from Desweek. So we build in their specific version of MineTwin a specific DCF importer, which interprets the way that they set up their Desweek plan, and it automatically creates everything for them, except the equipment parts, which we use the MineTwin internal libraries, where we also update this based on the expert opinions, because this is a greenfield project, right? The mine was operated many years ago. There's no way to estimate what will the conditions be like, what is the failure rates, what planned maintenance do you need for those mining conditions. And the plan for the ore and the waste also comes from this week. So in MineTwin, we've got this scenario editor, so you can see all the data pieces, and here's just a mapping of how what we require fits into the different parts inside the scenario editor. And I'll show a demo of how we can change these things. So if we get to the demo, you can see here the custom version that we've got of MineTwin, which is bespoke for Cornish Metals for that specific mine. If we start off, MineTwin is just blank. And then we import, in this case, an Excel file for the scenario file. And there you can see on the left-hand side a scenario editor with all the data inside. You can change some of these things inside the UI, save another scenario file if you want to. Some of the data you're able to edit inside Excel. So for example, the plan, it's easier to just copy and paste it from where you've got it. Save it, upload it immediately back into MineTwin. There's a nice 3D view at design time. You can make sure everything is set up correctly. The blue parts there was the stopes. And then when you go into the simulation mode, you can view that exact same 3D inside the editor as well. And this is great for verification and validation, to say a truck picked up material here and it drove 3 levels up to deposit it. Is that how it works? Right? We'll view this with the actual shift bosses. And you can actually do this in 2D as well. So what Andrey showed there for the mining method, where we drilled the holes up, you'll see that in a couple of seconds. Material falls to the floor and it gets taken out. You can see that green part now, they're drilling. Then it turns red for the charging, blasting, and the materials on the floor. So in MineTwin, we create a schedule for every piece of equipment, right? Based on some scheduling algorithms that we've got. And then we create the schedule, but the schedule also gets executed. So I quickly just want to pause this one here. So the orange bar and everything on the right-hand side of that line is actually the schedule that gets created. But when you schedule something to do haulage, for example, haulage is made up of a bunch of steps. And so the colored blocks that you see here on the left-hand side of the vertical line is the actual steps to do haulage, right? There's drive to the location. Then you have to maybe wait inside the queue, so you wait for your loading. Then you get loaded. Then you drive to the unloading area. Then maybe there's a queue as well. So you have to wait for unloading, then you do unloading, then you repeat that cycle. So in detail, you can see exactly what everything is doing at every given point in time. And this is great for validating the model to make sure that the behavior is correct. So you can see how it's executing the plan. If you've set it to reschedule, it'll do that as well. And all those different colored boxes that you've seen there gets put onto the stack chart, so you can see the percentage of time it's spent in any state. We record the routes of every piece of equipment. You can see the elevation there in the red line. What's the tons was transported on this route? What's the cycle times? There's an incredible amount of detail that we save and store and provide statistics on in MineTwin. So in terms of the studies functionality, which I briefly mentioned, there's a lot of pre-designed or pre-created experiments. So for example, the constraint analysis, fleet sizing, etc. You just right-click on that scenario, you can create these studies experiments. Then you can either run it locally, you can run it on the server, it keeps on sending the results back to you as it makes progress. You can see the first set there is our constraint analysis. The bottom part is an incremental fleet size analysis, so it's a dynamic experiment. It keeps on adding one more version of the piece of equipment that was most utilized in the previous experiment run. And for all of these studies, we also have pre-configured reports. So we're creating the scenario summary report. It tells you what did you do in your experiments, what was the result, some initial recommendations and findings. And this is really condensing that last part of the project phase that I've shown immensely. So if we talk a bit about the verification and validation, we did single process validation with the South Crofty team, where we simulated just a single production scope, single development scope, and they had a look at the animation, the scheduling, the execution thereof, the key performance indicators, going through all the steps, drilling, charging, blasting, etc. And they verified whether that is the correct behavior that they expect in the future, right? Because the mine's not operating yet. We also did some collaborative model checks with internal team members, simulation developers, mining experts. We reviewed it with the South Crofty team as well. And then to validate the model on a higher level for longer term with all your stopes and all your ore passes and everything in, we had to use ratios for validation, right? We can't use the total tons, because that's the question. Is our tons, waste, or utilization, is that correct? So we can't use that for comparison. So how do we validate this model? So we use these stable efficiency ratios, like tons per meter drilled for production, because regardless of the amount of tons, that ratio should still hold true. And the same for things like roof bolts per meter developed. We also used like average distances per trips for the loaders and the trucks. The distance between the stopes and the CDP should more or less be the same regardless of the tons that you mine, as well as for the distances for the trucks from CDP to ore passes. And you can see that it's actually quite accurate within single digits percentage differences. So a big study that we did for them was on this fleet sizing analysis and verifying whether they've got the right equipment plan. Because if you make a mistake here and you have to reorder another piece of equipment, it's going to put your plan back months, right? So here we did this analysis, loaders on the rows and trucks in the columns, and you can see that the system is more sensitive to loaders than trucks. So if you go from the top down in the rows, you can see the color indicating the volume changes more rapidly, right, for every column. Where on the trucks, if you go from left to right, it just changes between 3 and 4, like red to yellow, and thereafter for a single row it doesn't change a lot. So the system is way more sensitive to loaders than to trucks, right? So that's where you need your buffer capacity. And so adding 5 additional trucks doesn't provide a lot of benefit. In fact, if we go past 5, 6, 7 trucks, we can see for the same row, the volume is actually deteriorating. So we not only get diminishing returns, but we also see dynamic queuing and congestion, etc. So you don't want that many trucks because they end up waiting for each other and blocking each other, and you don't get a nice cycle time for the loading, for the hauling. And so the question was like 11 loaders, 5 trucks, 10 loaders, 6 trucks. It gives you more or less what you need, and that's a question for the mine to decide based on the economics. And for the specific year that we tested, will you be able to use it the following year based on your plan, etc. The last one where we spent a significant amount of time was on the surface handling part. So the plan configuration fell short of the target. So we've got the first one, there's 150 tons per hour crusher, then the base case, which is 200 tons per hour crusher, and we're like 200,000 tons short of the target. So our first set of experiments, we increased the hopper size at the crusher, additional loaders, increased the crusher size. They were close, we made some improvement, but we didn't get there. And then we had the second set of scenarios. So we tested increased hopper sizes and auto loading, again increasing the hopper sizes. And towards the end, you might see there's like 100% availability. Then we hit the target. So again, to Andrey's example, why you need simulation. And then the 100% isn't really achievable. So the last two ones there is with a 250 tons per hour crusher or a 200 tons hopper. That's the only way that you could reach the like material handling requirements, getting material out to surface to the processing plant. So that was a key thing. That was if we didn't do this work, right, by the time you start up and then you realize all the problems that you'll have, it would be way too late to now purchase additional equipment, change your plans, change your commitment. And there's a lot of stakeholders that we've shown in the first part of the presentation that relies on reliable commitments for this project. So just a summary of the key simulation results. we also advised them on 3 additional loaders during the first development year. So during this year, before the hoist is operational, certain tunnels inside the mine can't take trucks. So we're also considering equipment restrictions within specific pathways inside MineTwin. And so the loaders had a significantly increased workload. So it was like 3 additional loaders, not 1 or 2. So it's a significant change to that first initial year. But that's when you start up the mine, so it's really critical that they've got these pieces of equipment. We also did an optimized assignment of loaders and trucks to the levels pre-production phase. So when you start off the mine, not all the levels are connected. And where you take the machine down, you take it down in parts, and then you assemble it on that level, and then it lives on that level. You can't move it somewhere else when it's needed, right? And the static plan didn't consider that. So we helped them identify on which level, which pieces of equipment should be set, until you at least connect all the levels and they can move between the different levels. Okay, an additional loader that was required in year 5 to meet the targets, and then the surface material handling capacity was insufficient because that static plan couldn't consider this dynamic interplay between the truck and the loader unavailabilities, equipment timing, limited coordination. So to buffer yourself against that, you need to increase the hopper size, use the auto loading, or increase the crusher capacity. So there's also some new adjustments now to that part, which we're going to be testing in this current phase of the project that we're in. So I think that's it. Thank you from our side, and thank you for the South Crofty team for allowing us to present this as well. Any questions?
Thanks, Jaco-Ben.
I do have a question. On the, you talk about building out the schedule, like there's a pre-processing phase of the model. What level of detail does the schedule like that go into? Is it more what loaders are going to be in which locations, or is it the individual cycles you expect to happen and when you'd expect them to happen?
Do you want to? Okay, so it's not pre-model run, it's during model run. So at the start of every shift, the model considers what's the current state of every piece of equipment, what's the current state of every stope, and what's the targets that we're trying to reach, and then it develops the schedule. And basically what it does is it assigns pieces of equipment to high-level tasks. So it's saying 2 loaders and 3 trucks to transport material from this CDP to that ore box.
Yeah, so it's not saying it's going to move back and forth at this time, it's this is what you're going to do.
Yeah, this is what you're going to do, and we think it's going to take you 3 hours to do it based on some static calculations. And we can re-evaluate that if you change that setting to re-evaluate it during the shift time.
If it's late, it will push forward certain parts of the schedule.
Yeah, and then some things that might have been scheduled here at the end now gets cancelled, or there was an unplanned breakdown, and now the equipment sits and waits for that breakdown to continue.